So far we've added together vectors that are in the same plane, one-dimensional, as well as perpendicular vectors. What happens when we want to add together vectors that are both two-dimensional though? This makes it a bit tricky. Don't fret. We can always fall back on our old idea of the fact that we can always do tip to tail. You'll never go wrong if you do tip to tail. So let's do tip to tail here. Right, let's do tip to tail here. So I can do tip to tail. So I'll copy paste this one. I'll get this vector. I'll do tip to tail. So that's my tip. And let me match the tail of the second red vector to it. Okay. And now here comes the magic. Okay, so this so far doesn't look very useful. We do know that the resultant vector is from the, as it always is from the very origin, so from the very beginning tail, or the very origin to the very end here, right? If we follow the kind of arrows, we can have that direction. So I'm going to draw my resultant vector from the very tail to the very tip. That's going to look like this. And hopefully you can visualize this. This might be like if I drove 30 meters at, if you imagine this is like kind of looking down on a map, if I drove 30 meters in a kind of northeasterly direction, and then drove another 40 in a more northerly direction. And so that's going to be my overall resultant vector. The problem is I can't really easily get the answer to this r. It's a bit difficult for me to know how long this r is. Thankfully, we have a trick up our sleeves that will allow us to determine this resultant vector. And it all comes down to what we did last time, which is when we add together perpendicular vectors. So before we go any further, I want you to focus and concentrate on this blue vector here. So let's grab this blue vector and let's analyze it in a bit of detail. So this blue vector, we saw before that when you added together two vectors, you could produce a new angled vector, right? So for example, we could remember that if we added a vector like this plus this, we could get a vector that looks something like this, right? Because what we would have, is we'd have the red vector kind of lying across like this, and then the green vector kind of adding together like that, and then our resultant vector would look something like this, right? Something kind of angled like that. And so we're actually going to use the reverse of that logic, right? And we're going to do something called vector decomposition. Vector decomposition, which sounds very scary, but I promise you it's not that bad actually. So what we've done before is we've gone this way. We've gone from two individual vectors and we've added them together into an angled vector. What vector decomposition does is that it goes in the opposite direction. So we go from a nice, angled vector back into perpendicular components, right? And that makes sense. You can imagine if I added two numbers together, 2 plus 3, it gives you 5. I can go from 5 and I can say, hey, look, this 5 is made of a 2 and a 3, right? So that's all vector decomposition is. So let me grab this vector and we're going to perform vector decomposition on it, right? So this vector, so we can always decompose a vector into its x and y components. So we can see its x component here, right? And its y component here. So you can imagine that if I was to grab this red component and I was to grab this green component and I added them together, well, what would I get? Well, if I again did the tip to tail thing, I would quite literally get the exact same vector, right? You can see that it's going to be the exact same length, exact same direction, and that's the point, right? We want to find these components such that when you add them, you get back the original vector, right? It's just like if you have the number 5, we want to find the components of 5 you know, something plus something, that when you add them together again, it gives you 5. In this case, it might be 3 and a 2. Right. So now the tricky part is, let's actually be able to figure out what this red and this green thing are. Thankfully, we can use the power of trigonometry. So let's figure out this red one first. By considering this triangle here, we can have a look at here and we'd say, okay, look, we can probably do a little bit of trick here. So if I bring this down, we can probably say that cosine 20 is equal to, let's call this adjacent, adjacent over our hypotenuse of 30 meters. So that means our red vector A is going to equal to 30 cos 20, which is going to equal to 28.2 meters. So I can say that this is going to be 28.2 meters. I can do the exact same thing for the green vector. So I can say that, I might say sine 20 is equal to my opposite over my hypotenuse, which is 30. And so I might say that my opposite is equal to 30 sine 20. That's opposite, that's not 0. And 30 sine 20 is equal to 10.2. 10.3. So this is equal to 10.3 meters. So that's our vector decomposition. And if you actually just want to quickly check that this does indeed give us back our blue vector, all you would need to do is you just need to put in your 28.2 here and your 10.3 on there. And if you did the same vector addition steps that we've done before, you will find that this blue vector, it will be exactly 30 meters, and the angle there will be exactly 20 degrees. You go for it if you want to try that. But that's the critical part, right? So vector decomposition. We can decompose a vector into its x and y components, because when those x and y components add together again, it forms that same vector, right? So now that we understand vector decomposition, let's get back to our diagram here. What I want to do is I want to decompose our vectors here, right? So I want to decompose our vectors. So I'm going to split my blue vector into an x and a y component, and I'm going to split my red vector into a x and a y component as well, and I'll show you why in just a tick. Cool. So I have my x and my, I've split them up. Now let's see what's going on. I'm going to do a bit of rearrangement, and I'll show you exactly what is going on. So what I'm going to do is, so we recall that vectors can be moved freely. It doesn't matter, we can move them freely, it doesn't change anything. I can move this one down here, and I'll move this one to be there. And so what can I say? So we no longer need these solid lines, because this solid vector is when you add this together, these blue ones and these so when you add together these blue ones, you do get this big blue one. So I'm going to delete that one. We don't need it anymore. I'm also going to get rid of this big red one, because again, if you add together these red pieces, you're going to get your overall big red vector. So we don't need these anymore. And now you can see that the question has been simplified dramatically, right? We no longer have these two weird angle vectors. What do we have? Well, all we have is we have a 1x vector, right? So I can draw this in a new color, let's say purple, right? One purple vector. And you could easily figure out the length of this purple vector. This is what we did in the first video, adding together two vectors that were in the same direction. That's easy for us. Similarly, this vector, we could easily add together this red and this blue vector. Let's say that we can form in our purple vector here as well. Oops. With these two purple vectors, we simply use the thinking that we explored in the last video when we added together perpendicular vectors, and we can find out what the length of this green vector is, and we can figure out what the angle here is as well. So let's actually try that, right? So now we know the methodology. Let me write that down for you, right? So let me write the methodology down for you. So the first step will be to decompose our vectors. Decompose our vectors. And then what do? We add together the x components, right? So add x components. Add x components to become one vector. To become one vector. We'll do the exact same thing for the y, right? So that's what we did here. We added together those y components. And then our last step is to add x vector plus y vector. So this step number 4 is when we are adding together these two purple vectors. Right? That's what we're doing there in the fourth video, in the fourth step there. Now that we have the general gist of that, let's have a go and actually do it on this example here. So let me also grab the steps to remind you. So let's do step number 1, which is we're going to decompose the vectors, right? So we're going to decompose the vectors. So this part is going to become, so this on this horizontal part, we can say that cosine 20 is equal to the adjacent over the hypotenuse of 30. So adjacent is equal to 30 cosine 20. This one's the opposite, so we can say that sine 20 is equal to opposite over hypotenuse. So therefore the opposite is equal to 30 sine 20. Now, we can put that there. Now, once you do a couple more of these, you'll begin to realize that if you want the horizontal part, you'll use cos, and when you want the vertical part, you'll be using sine. So we can actually skip a bit, and we can say here this is going to be 40 cos 60 and 40 sine 60. This is just to speed things up. If you're not comfortable with this, I highly encourage you to just do the trig stuff again. That's fine. Okay, so we've decomposed all the vectors. Now what do we do? Well, what we want to do is we want to add together those x components, right? So if you remember what we did, we no longer need these big vectors. We now simply add together the x components, right? So we no longer need these guys. So I'm going to move this guy down, and the value, move this guy aside, and his value. We don't need these guys anymore. The big vectors have done their purpose. No need for them to exist anymore, right? So now what I'm going to do is I'm going to try and sum together the x components, right? And this is very easy, right? So I can say that sigma x is equal to, we want to add together those two vectors. So you simply do 30 cos 20 plus 40 cos 20 cos 60. And what do we get? We get 48 meters. Great. Let us now do the same thing for sigma for the y direction. So we can do sigma y. So we can add together these two vectors. Sorry, I should probably give that old vector a direction as well. It's 48 meters towards the right. And so this is going to be 44.9 meters upwards. So now that we know this, now we simply add together, step 4, we add the x and the y vector together, right? So if you imagine, what we are going to do is we've replaced these components with so step 4, add x, y components. So I'm going to add together the x and the y components. So I have my 48 meters. So I have my 48 meters. And I have my 44.9 meters upwards. This is from my y-axis. 44.9 meters. And now, to finish it off, we just need to figure out what the length is and what the angle is here. So we can see that via r squared is equal to square root, r squared is equal to 48 squared plus 44.9 squared. So we can see that the length of the resultant vector is going to be the square root of 48 squared plus 44.9 squared. And that is going to give us 66 meters. And the second part will be for us to figure out what the angle is. So for our angle theta, we're going to have tan theta is equal to 44.9 over 48. So theta is equal to tan inverse of 44.9 over 48 is equal to 43. Okay, cool. That's about it for adding perpendicular vectors. In the next video, we'll have a look at some examples, and then the one after that, we'll have a look at how do you add vectors that are, how do you subtract perpendicular vectors. I'll see you then. We offer physics, chemistry, and math tutoring. For more insightful explanations like this one, head to tutorgum.com.